An international race is picking up speed to see our universe for what it really is and how it came to be. According to the standard theory that describes the origins of the universe, its early moments were marked by the explosive contact between subatomic particles of opposite charge. Scientists are now focusing their most powerful technologies on an effort to figure out exactly what happened. Our understanding of cosmic history hangs on the question, how did matter as we know it survive? And what happened to its birth twin, its opposite, a mysterious substance known as antimatter? A crew of astronauts is making its way to a launch pad at the Kennedy Space Center in Florida. They'll enter the Space Shuttle Endeavour for the 134th and second to the last flight of the Space Shuttle.
Be back here June 1st.
Little noticed in the publicity surrounding the close of this storied program is the cargo bolted into Endeavour's hold. It's a science instrument that some hope will become one of the most important scientific contributions of human spaceflight. It's a kind of telescope, though it will not return dazzling images of cosmic realms long hidden from view, the distant corners of the universe, or the hidden structure of black holes and exploding stars. Unlike the great observatories that were launched aboard the shuttle, it was not named for a famous astronomer, like Hubble or the Chandra X-ray Observatory. The instrument, called the Alpha Magnetic Spectrometer, or AMS, is the brainchild of this man, Samuel Ting, from Massachusetts Institute of Technology. At the heart of the AMS is a large superconducting magnet designed to operate in the pristine environment of space. With its intensive power requirements, the final version was attached to the International Space Station. The promise surrounding this device is that it will enable scientists to look at the universe in a completely new way.
And you guys are go for SRMS release. Endeavour copies on the big loop.
Most telescopes are designed to capture photons, so-called neutral particles reflected or emitted by objects such as stars or galaxies. AMS will capture something different: exotic particles and atoms that are endowed with an electrical charge. Among these are a theoretical dark matter particle called a neutralino. Then there are the strangelets, a type of quark that could amount to a whole new form of matter. The instrument is tuned to capture cosmic rays at high energy, hurled out by supernova explosions or the turbulent regions surrounding black holes. And there are high hopes that it will capture particles of antimatter from a very early time that remains shrouded in mystery. The chain of events that gave rise to the universe is described by what's known as the Standard Model. It's a theory in the scientific sense, in that it combines a body of observations, experimental evidence, and physical laws into a consistent overall picture. But this picture is not necessarily complete. The universe began hot. After about a billionth of a second, it had cooled down enough for fundamental particles to emerge in pairs of opposite charge, known as quarks and antiquarks. After that came leptons and antileptons, such as electrons and positrons. These pairs began annihilating each other. Most quark pairs had annihilated by the time the universe was a second old, with most leptons gone a few seconds later. When the dust settled, so to speak, a tiny amount of matter, about one particle in a billion, managed to survive the mass annihilation. That tiny amount went on to form the universe we know. All the light-emitting gas, dust, stars, galaxies, and planets. To be sure, antimatter does exist in our universe today. The Fermi Gamma Ray Space Telescope spotted a giant plume of antimatter extending out from the center of our galaxy, most likely created by the acceleration of particles around a supermassive black hole. The same telescope picked up signs of antimatter created by lightning strikes in giant thunderstorms in Earth's atmosphere. A European cosmic ray satellite called Pamela detected a huge store of antiprotons in orbit around the Earth, created by high-energy particles striking the upper atmosphere, then held there by magnetic fields that ring the planet. Scientists have long known how to create antimatter artificially in physics labs, in the super-hot environments created by crashing atoms together at nearly the speed of light. Here is one of the biggest and most enduring mysteries in science. Why do we live in a matter-dominated universe? What process caused matter to survive and antimatter to all but disappear? One possibility, that large amounts of antimatter have survived down the eons alongside matter. That was the view of the German-born physicist Arthur Schuster, who appears to have coined the term antimatter in 1898. He imagined that its opposite charge would allow it to act as a counter to gravity. Large tracts of space, he wrote, might thus be filled, unknown to us, with a substance in which gravity is practically non-existent, until by some accidental cause, such as a meteorite flying through it, unstable equilibrium is established, the matter collecting on one side, the antimatter on the other, until two worlds are formed, separating from each other, never to unite again. The issue gathered dust until 1928, when a young physicist, Paul Dirac, wrote equations that predicted the existence of antimatter. Dirac showed that every type of particle has a twin, exactly identical but of opposite charge. So for every proton, there's an antiproton. For every electron, there's a positron. For every neutron, an antineutron. Within them are quarks, and their twins, the antiquarks. As Dirac saw it, the electron and the positron are mirror images of each other. With all the same properties, they would behave in exactly the same way, whether in realms of matter or antimatter. In his Nobel Prize lecture in 1933, Dirac pondered a larger reality for antimatter. If we accept, he said, the view of complete symmetry between positive and negative electric charge so far as concerns the fundamental laws of nature, we must regard it rather as an accident that the Earth, and presumably the whole solar system, contains a preponderance of negative electrons and positive protons. It is quite possible that for some of the stars it is the other way about, these stars being built up mainly of positrons and negative protons. Just the year before, the physicist Carl Anderson had confirmed the existence of antimatter by shooting gamma rays at atoms, creating electron-positron pairs. It became clear, though, that ours is a matter universe. The Apollo astronauts went to the moon and back, never once getting annihilated. Solar cosmic rays proved to be matter, not antimatter. Traveling to every corner of the solar system, our probes have not encountered any objects made of antimatter. Cosmic rays from the Milky Way are overwhelmingly matter. If there are any large concentrations in nearby galaxies or galaxy clusters, we should see gamma rays produced when particles and antiparticles find each other. It stands to reason, too, that when the universe was more tightly packed, that it would have experienced an annihilation catastrophe that cleared the universe of large chunks of the stuff. Unless antimatter somehow became separated from its twin at birth and exists beyond our field of view, scientists are left to wonder, why do we live in a matter-dominated universe? Dirac's symmetrical view of matter and antimatter, which saw them as equivalent, collapsed 3 decades later in 1964. The American physicists James Cronin and Val Fitch examined the decay of a particle called a kaon to its antiparticle twin. They found that the transformation back to normal matter did not occur with the same probability. That would suggest there must be small differences in the physical laws that govern matter and antimatter. To find out exactly what makes them different, or asymmetrical, would be a big step toward understanding how our universe took the shape that it did. That's why physicists are hot on the trail of antimatter, with new technologies designed to give them a closer look at this strange substance in nature and in the lab. What if there is some antimatter out there, escapees from the mass annihilation of the Big Bang, still fleeing through the emptiness of space? The crew of Endeavour placed the AMS instrument on the International Space Station in May 2011. Since then, scientists have been combing the data for the signatures of antimatter particles striking its detector. If they manage to detect heavier elements such as antihelium or anticarbon, that would point to concentrations of antimatter in space large enough to have formed stars where those elements are created, and suggest that symmetry, may not have been broken after all. Such heavier anti-atoms can exist. At Brookhaven National Lab in New York, scientists recently smashed gold atoms together at nearly the speed of light. From about 1 billion individual collisions, its detectors recorded the presence of 18 antihelium atoms, atoms with 2 antiprotons and 2 antineutrons. The explosive potential of antimatter in this universe has long animated the voyages of science fiction. It's the fuel of choice for getting beyond our solar system and out to the stars. Just to get into orbit, the space shuttle had to be loaded up with some 15 times its weight in conventional rocket fuel. The energy contained in antimatter is orders of magnitude greater. In fact, it would take just a coin-sized portion to propel the shuttle into orbit. Because antimatter is so volatile in our matter-filled universe, the challenge for scientists is first to create it, then to hold it for enough time to study it, before it simply vanishes. Even as the shuttle Endeavour glided onto land for the last time, AMS scientists were beginning to filter through the rush of charged particles in space. Meanwhile, scientists on the ground were beginning their own intensive efforts to corral antimatter in their labs. They are trying to do this at the giant European Physics Lab, CERN. In a little-known corner, the Anti-Proton Deceleration Lab, a group of scientists is showing that you can actually trap and hold antimatter long enough to study it.
The antiprotons from the antiproton decelerator, that's the machine that we need here at CERN, come down this pipe right here. And they come into our apparatus, which is inside this large magnet. This is a very strong magnetic field to help to confine the charged particles that make antihydrogen. We mix the antiprotons with positrons inside this magnet trap, and that's where we capture them.
Inside the alpha chamber, the magnetic field holds the particles in place and isolates them from one another. An electric field separates the electrons and positrons. They are then carefully brought into contact. When 2 positrons collide, one falls into orbit around an antiproton, forming antihydrogen. Then the molecule is trapped by magnetic fields, like a marble rolling around in a bathtub. Now remove the bathtub, the magnetic fields. The antimolecule smacks up against the wall of the detector and annihilates, emitting a shower of particles.
So what we do is hold on to them for 1,000 seconds and then release them to make sure they were there. That's how you do this measurement.
That 1,000 seconds, almost 17 minutes, is a major accomplishment.
On the atomic life scale, 1,000 seconds is forever. Things on the atomic life scale are measured in nanoseconds or smaller perhaps. So this is forever for an atom to be trapped. The next step, and that's what we're reporting now, is to hold on to it. See how long can we keep it around so that we can study it. After all, that's what we want to do. We want to study the antimatter, compare it to matter, and see if they're the same. And by study, we mean interact with lasers or with microwave radiation to see what their structure is inside. How do they behave? Do they behave exactly like hydrogen?
Within the same lab, the effort to pinpoint differences is already underway. Scientists working with the Asakusa detector are trying to measure the precise weight of an antiproton. These oddball molecules contain one antiproton, which would normally inhabit the atomic nucleus. Instead, it orbits the nucleus in place of an electron. It survives microseconds in the detector, but that's enough for the scientists to hit it with a pair of lasers. The molecule blows apart on impact, and that enables them to calculate the weight of its components.
We've measured to a precision of 9 digits. And we found that the antimatter, the antiproton mass, is exactly the same as the proton mass, so therefore 9 digits of precision.
If they find there's a difference, it's bound to be subtle. Will it be enough to shed light on why matter survived and antimatter did not? The differences may lie much deeper in the structure of matter than we've so far been able to go. Scientists are now preparing to throw a new generation of powerful technologies at the problem. At the Large Hadron Collider at CERN, they can send atoms whipping around a 27-kilometer tunnel and into ultra-high energy collisions. Looking at the zoo of particles that splatter onto the walls of the detectors, they are hoping to find differences between quarks and their anti-quark counterparts. One recent computer calculation performed at Columbia University unveiled differences between quarks and antiquarks when it was assumed that these particles interact with dimensions beyond the 4 that define the universe we experience. Still, its authors wondered whether the differences are enough to account for our matter-filled universe. Understanding the asymmetry between matter and antimatter is one of the most important quests in modern cosmology, because it would help expand, or perhaps even challenge, aspects of the standard model. The clash of these opposite forms in the early universe harks back to William Blake's poem. What immortal hand or eye could frame thy fearful symmetry? We now ask, what in the chaotic birth of time and space could break nature's symmetry and set our universe in motion?